Layout of a proof, opposite sides of a parallelogram. I'm going to take a step back and show you the whole board. Okay, we have our drawing. We have our proof table with the statements on the left and the reasons on the right. We have our given, which is our evidence. We have the thing we're trying to prove. Okay, so let's take a closer look at our drawing. We've got a parallelogram. Okay, now ignore these hash marks in here. That's for in a couple seconds coming up. But you can see it's a regular parallelogram. Those are parallel, those are parallel. Okay, and it's parallelogram A, B, C, D. Okay, this is angle A, that's angle C. Let's see what we're trying to prove. Well, the given is that AB is parallel to DC, okay? And that line AD is parallel to BC. Okay, well, it's a parallelogram, we know that. We need to prove that AB is parallel to DC, or is congruent to DC, that AB is congruent to DC, and that AD is congruent to BC, okay? Now, if you remember from our past proofs, what better way to prove congruencies than to use CP/CTC, which is explained in video 112, or the ASA rule, which is video number 104, or the reflexive property, which is also identity property. So I would draw a diagonal from angle A to angle C and make two triangles so that we could use these, okay? So I'm going to draw a line, a diagonal, and what that's going to do is create two triangles. That's going to help us prove things. Now you can see that that angle by A is congruent to this angle by C, and this angle by A is congruent to that angle by C. So here is our first statement. It's our given that these are parallel and these are parallel. That's given. These are parallel and these are parallel. And that angle ACD, that's this little one hash mark angle right there, is congruent to BAC. That this is congruent to that. And that DAC, the two hash mark one, is congruent to that one, A to BCA, okay? Our reasoning for that is, if you remember back in video number 20, we talked about transversals. And there was a postulate that mentioned that alternate interior angles of two parallel lines are congruent. So we've now proven two angles are congruent. This angle and this angle. We got two angles now that are congruent. Good job, right? So now we're going to say that AC is equal to AC, because it's a shared line for the two triangles. And that's reflexive property or identity property, okay? So now we've proven a side is equal. We got two angles equal and we've got a side equal. Well, guess what? Two angles and a side. We can say that ADC, the one on the triangle on the left, is congruent to the triangle on the right, and our reasoning is angle side angle. We've proven the two angles on the side, so now we're stating it. That was the ASA rule, the angle side angle rule, is in video number 104. So now we stated that we've got angle side angle congruent. So now we can say that AB is congruent to DC, AB is congruent to DC, and that AD is congruent to BC, that this one's congruent to this one. And why? Because of the CP/CTC rule, the one that was in video number 112. It says corresponding parts of congruent triangles are congruent. We've proven that the corresponding parts are equal, that they're congruent. Very simple, very methodical coming down. That's how you do an opposite sides of a parallelogram proof. Our next proof is going to be opposite angles of a parallelogram in video number 121. Very similar to this one. I'll see you there.